Today we are going to do section 5.7, change of variables, in which case we're going to talk about the Jacobian. I should mention first that after Theorem 5.14, I'm planning on skipping the rest of the section. The reason is because the Jacobian refers the transformation process, which is not covered properly in this section, because transformation is usually taught after calculus, and but you need it to do the Jacobian. So what your book decided to do is just I don't know, skim through it and hope that you understand it anyway, which I don't agree with that approach. Okay, so the second half, roughly the second half of the section, we are gonna skip it because once you learn how to do the Jacobian, you just need to know how to do transformations, and then the Jacobian will be a cinch. So there's no real reason to do the Jacobian unless you know how to do transformations. That's actually the tough part. The Jacobian is the easy part. Maybe that's why the book decided to do it here and figured they'll just teach you the easy part, but you really shouldn't be doing it. You need to know the tough part too. Otherwise it's like teaching you to walk on one leg. It's just not going to happen. Okay, so that's our plan for today. So first, let's look at transformation. We'll go over transformation in just enough to tell you what it is. A transformation is when you have two regions on the plane. See, you start with a plane in the UV plane where you have a point that's called UV. A transformation is a function such that x and y are defined in such a way that x is a function of UV and y is also a function of UV, and the functions will give you a new value, right, of xy, which you plot in a new place, and that's called a transformation. So that it just takes something from the old, here's the old one, okay, that's and to something to the new place. So having said that, please do example 5.65 as part of your homework. Oh, I should first mention that a transformation is considered one-to-one if each point lands in its own unique point. No 2 points lands in the same spot. Okay, so when they jump, everybody got a spot, got their own spot to jump to. See, that when UV jumps over to XY, they're not going two of them are not going to smack into this together because they landed in the same spot. If that is the case, it's called a one-to-one transformation. To show that something is, or to check if a transformation is one-to-one, you just pick two random points and then see if they end up being, see what happens if they're equal. If the end result is equal, then the 2 points has to be the same point. They have to be equal. So that's how you can prove something is one-to-one. So if you can prove that they are equal, if anything that lands in the same spot has to come from the same spot, then it is one-to-one. If you can show a single example where two different points land in the same point, then the transformation is not one-to-one. So please do example 5.65, and then I'm going to talk about example 5.66. Now example 5.66 is a transformation where we have TUV, okay, T takes points in the UV region and then smack it into the XY region. So T is a transformation, and the rule of transformation goes like this. For X, the new X is you take the old U and V and do this to it, and Y, you take UV and multiply it together. All right, so let's look at page 613, the next page, and we have two regions. Okay, one region I've drawn right here. What we're trying to do now is determine what does this shape become in the new plane after the transformation, and your book decided not to bother that much explanation, but so I decided to draw the parametric form to show you how this works exactly. Now what happens is, first let's consider the line A. A just goes from here to here, the vertical line, and we'll represent it parametrically as, with the parameter t, such t goes from 0 to 1 always, okay? So the line A, as you can see, can be represented as 0 comma t. where t can go from 0 to 1, right? X coordinate is always 0, y coordinate goes from 0 to 1. That describes A. And then similarly, B is tt, right? X and y are the same, and that gives you the y equal to x line. In this case, the u equals the v line. That's B. And C, similarly, C will be t comma 1, because C, the y value is always 1. The x value can go between 0 and 1. So that's a parametric representation of the line C. Now, if we stick t in there, or let's put it this way, if we use t on these things, so what are the rules of t? Rules of t are that x coordinate is u squared minus v squared. Okay, this is u and this is v. Maybe I should write that down. All right, this is u, v. All right, so now applying that rule then of x equal to u squared minus v squared, so u squared minus v squared would be minus t squared. That's the x, okay, after the transformation. So, and then uv is y, uv is just 0. So we get 0 here. So then the line A, as t goes from 0 to 1, will be transformed into A prime, okay, which happens to be down here. As t goes from 0 to 1, the x coordinate goes from minus 1 to 0. The y coordinate stays at 0. So this is the new A, which we will call A prime under the transformation. Now the other lines we'll do in a similar way. B is tt, so u squared minus v squared will be 0, right? And then uv will be t squared. And 0 comma t squared is this thing. T goes from 0 to 1, right? So x coordinate is 0, 0 to 1. So you end up with this is b prime. Is this thing right here as t go from 0 to 1. And then lastly, C is t comma 1, and apply the same rule, u squared minus v squared. That will give you t squared minus 1. And then the y coordinate is u times v. U times v is just t. So the new C line, okay, under the transformation is parameterized by t squared minus 1 and t. And if you plot that out for t is going from 0 to 1. So then it goes from 0, okay, and when it's 0, it's at minus 1, and then go all the way up to, when it's 1, it will be 0, 1. See, so it's as you can see, there's a square here, so it's a sideways parabola in the parametric form. So here's your parabola that going to the side. It goes the parabola that goes like this, and that is the C line. So as you can see, the region is being mapped. The boundary of the region, at least, is being mapped by t this way, okay? And then the points, you can plug in the points in this formula and get the same thing. 0, 0 will be mapped here, and then 1, 1 will be mapped to 0, 1 up here, and then 0, 1 will be mapped to negative 0, 1 right here. So the whole thing kind of turned, you kind of take the whole thing, turn it down by 90 degrees or so, and then this B, let's see, no, C, C got bent into that shape, okay? And then, well, I'm not going to explain why that is, but I'm going to simply argue that everything inside will also map in here, okay? Now that we found the boundary, we'll just make the leap. Like I said, the transformations are taught after calculus. I remember taking it in various classes afterwards. So we're not going to go into details why this is the case. We'll just do the boundaries and then we'll call it done. All right. So that is, I think that's how we're going to do this. And that's the example 5.66. Please redo this as part of your homework. Figure out how to parameterize the lines, and then you can follow the formula properly and see how everything works. It will basically want you to just stare at it and understand it or something. And that's because they're trying to avoid teaching transformation, because transformation can get very, very complicated. But we do need to, I think we should at least go over this much in order to get a decent understanding of what a transformation does. And so, and So that's that. Next, let's talk about the Jacobian. But before we talk about the Jacobian, I want to remind you some formulas some theorems that we had in the past. Now, to review some of the vector qualities that you might have forgotten or can't remember exactly, a vector-valued function is a function where r of t, the vector, is fti in the I direction and gtj. Now, f of t and g of t are just functions, and as t changes, then r goes about in space, okay, in one direction. And it's a space, well, in this case, it just goes on the plane because this doesn't have 3 directions. So I'll just go around on the plane in various ways as t changes. Now, there's one thing you should notice, that derivative of r is defined as just simply each component taking the derivative, f prime and g prime. And specifically, the derivative of r has a meaning. It's the tangent of r, okay? So then, the unit tangent is you divide it by its magnitude, but we don't care about unit right now. We just try to remember that the derivative of r is just its tangent. Now next, the cross product is calculated this way, okay? U cross v equal to all that stuff, see? And there's a bunch of multiplication and subtraction happening. But that is the cross product. And that another way of doing the cross product is the determinant. It's just a mnemonic device. That the cross product, you do it like it's a determinant and then cross it that way, and it's the same thing, right? And then in case you don't remember how to do the determinant, this is how you do the determinant. In case you don't know how to do the 2 by 2 determinant, the definition is right here, which is exactly this thing, which is why it's memorized that way. So that's the cross product. And one more thing I should mention is the area of a parallelogram. About, 500 pages ago, we learned that the magnitude of the cross product gives you the area of the parallelogram that's formed by the 2 vectors u and v, okay? And so that's that. With that, we are ready to study the Jacobian. First, the Jacobian, has to do, the first partial derivatives has to be continuous. And if that happens, it is called the C1 transformation. What I mean is, let's say the t is that transformation we looked at, okay, right here, t on this side. T is uv, guv, huv, etc., where x is the first component and y is the second component. Then you can take the partial derivative of g with respect to u. Okay, up here, okay, and the same as h with u and v, and so on. Now there are 4 partial derivatives, and they all need to be continuous to be called a C1 transformation. And that's all you need to know about that for now. Okay, and if the first partial derivatives are continuous, they happen to be called C1. Now next, let's look at a situation where we're going to do the transformation. We have a certain graph, okay, and we're going to transform it over here into something else, and through the process of t, and where t is given as whatever it is. Now, before we go any further, I want to show you what I wrote down as a sample so that you can see it more clearly. The sample is exactly the example we did a little while ago. X is still u squared minus v squared, y equal to uv, and tuv is our transformation, which equals to xy, where x is g, u, and v, and y is h of u and v. All right, so and specifically, I picked a point for u0, v0. I made it up. u0 is 3, v0 is 2, and if you plug it into these relationships, you will get that x0 will be 5, y0 is 6, and so on. And then so x, of course, is guv, which I also wrote down over here. And as a result, you can take partial x, partial u. Okay, which is also written as g u of u0, v0. We're calculating this thing at our initial points that I picked. So then if you plug everything in, you get, or take the partial derivative, that is just 2u. And then when u is u0, which I chose to be 3, that is the answer 6. Similarly, we can do partial y partial u. Again, y is uv, y is also called hu comma v. So then partial y partial u evaluated at these 2 points is also written as u u0 v0, and which is in our case happens to be just v, right? Take the partial with respect to u, that's just v, and plug it in v0 at v0, that gives us a number of 2. And next we're going to look at something different. Okay, this is a vector. We're going to define this vector by g and h, which is right here. Well, originally it's just x and y. Okay, here's our x, y. So we're going to define it as xi, y, j, which transforms, being the x is g u of v over there. And then we can transform it into this thing. So then it is also called g u v I, h u v j. Now so then we'll plug our sample here. In our example, x is u squared minus v squared, which is g u v, so we'll plug it in here. So our vector has the form of u squared minus v squared I plus u v j. And what is this vector again? This vector represents the result of our transformation. Here's our transformation, right? And it basically just rewrite it. Okay, so the vector is what happens is when you plug u and v, and the vector will be on the plane here, there, everywhere. And before, when I showed you the original vector, that was a line on the plane, right? The reason it's a line is because the vector I showed you in the definition, this is a vector based on one variable. Okay, so then the r of t, the vector function, is going to be some curve in space, line or curve. Whereas this one it has 2 variables. So this is going to describe a region, okay, which is what t does. T takes some region, as we've seen earlier, sort of like, and then push it into make everything land into a different region. So being that this has 2 variables, then this is a vector function that will end up being some region depending on u and v. All right, so that is the result of t. And next, what we're going to do is we're going to fix the value of v in this vector. That is, we're only going to consider for a fixed v at v0. In our case, v0, I chose it to be 2. So let's consider the vector that is the image of the transformation. What happens when you fix the variable, fix it at a specific number at 2? When that happens, then your vector becomes, we'll call it p of u, okay? Because v is now the constant, right, which is 2. So then we'll just call it p of u, because now it's a vector function that has only one variable, which means it's some kind of a line. And then so I wrote it out here. So if we fix v as v0, which is in our sample 2, then we'll plug 2 in v, and then we get u squared minus 4 for I and 2u for j. And so that we will call this function p of u, just because that's well, no reason. Anyway, so what is p? And then let's see. All right, the next thing we need to do is we're going to take the derivative of p with respect to u, okay? Because, well, the derivative, as you remember, the derivative of a vector function is simply the derivative of the components, the theorem 3.2, right? So we're going to take the derivative, and when we do, then we get, this is, for I is 2u, right? And for j is just 2. So that is the derivative of u. And as I mentioned, the derivative of u is the tangent. In other words, if here's the path of u, p of u, then the tangent is a tangent at that point, right? It's the same slope. So that is equal to tangent. Now, the derivative of u, which we did, is also called r with respect, the vector r with respect to u, which means we'll take the partial derivative of g with respect to u, because the with respect to u is the same as considering the v variable constant, right? Which is what we did here. We have the v variable constant as at 2. So that's the same thing as doing the partial derivative. The partial derivative of g of u is just 2u, right? It's the same as this. And similarly, the partial derivative of h of u is just the 2. And I just want to, because when we take partial derivatives, the other variable is held at constant for the moment. So then, all this stuff works out. And I'm also evaluating at u0, v0. Is it u0, v0? No, let me see. No, sorry, it's not u0. It's just v0, because we said that we're going to hold v0, but u is still moving around. So that is equal to just u, okay, the partial derivatives. And of course, the partial derivatives is the same as partial g of u is the same as partial x, because g is x. See, we have in this condition where we have different names for the same thing, so you have to remember all the stuff. So partial x, partial u is the same as g of u. If you hold, well, anyway, so li and then partial y, partial u of j. So that's what how this all comes out. And eventually, being that p prime of u is the tangent, then at x0, y0, then we have this is p prime. Okay, this line here is p, the vector, which is the same as r, holding v constant at 2. So that is a sample that I dreamed up of, and you might think, why do we need to look at this? It will help you understand the Jacobian. Now, I should mention that p of u, that is r u v0, takes the line v0 and then maps it to the line over here, which is p of u. And well, that's because r is a map that, but we're holding v at v0, which is 2 in our case. So that's how, just for this line, then it gets mapped over there with that as being the tangent. So let's, now that we know all this stuff, let's look at the Jacobian on page 614. The Jacobian is, first we have the same situation. We have a sample transformation that takes uv to xy, is being defined as g and h that way. Okay, now let's look at the next page. And similarly, we will define some kind of a vector r, where r will be defined as g u of v plus h u of v of something, and then the corner is being mapped where u0 v0 is being mapped over here as at x0 y0, which I haven't written down, but that is the same thing as here. See, here's a sample. Now next, what we're going to do is we're going to calculate the tangent vector. That is ru. Where is it? Now, here's p of u. The tangent vector where we hold v0 at constant is going to be equal to the derivative, okay, right here, which the book doesn't mention p of u, but this is just a sample. But the idea is that r of u, if we calculate the tangent vector at v equal to 0, is taking the partial derivative, which is a g of u, and we are, I guess this is, in this case, we're evaluating it at exactly 0, okay? So then, because we want to know what is it at x0, y0, so we are going to evaluate it at exactly 0, but we're going to take the derivative first, and then evaluate it at x0, y0, which is also the same as partial x, partial u, and partial y, partial u, both evaluated in this case at x0, y0, which is this point right here. I should probably write it down. This is x0, y0. This point, I mean, big fat point. All right. So then, and then similarly, we have, that's just a tangent partial derivative with respect to u. Where'd it go? Yep, our u. Now our v, that is the partial with respect to v, and then we go along this line, the idea is the same. That is, we have a q of v, okay, that maps this line up here, over here, and it has a very similar definition. The point is it'll map the vertical line into some other thing depending on the transformation. And the result of our v is exactly the same in a symmetrical way. Then our v is partial derivative of g with respect to v evaluated at u of 0, v of 0, etc., which end up being partial x partial vi and partial y partial vj. And so that's so far so good. Now the next one concept we have to think about is the definition of the partial derivative. The definition of the partial derivative by definition says that if you're taking partial derivative with respect to u, that means you hold v constant, right? And then you take the limit as delta u goes to 0. Now that equation can be rewritten as an approximation like this. This is the rewritten approximation. That is, that means the subtraction, the numerator is the same as the denominator, which is delta u times our u. Similar for our v, the exact same situation applies, except that now you're dividing by v, and so then is equal to partial u partial v. So now we have, what are we doing in here? What we're doing is that we have a very small rectangle where the length is delta u and the height is delta v, and this line here is v equal to v0. And except for it being small, there's no difference between that graph and this graph. Okay, that's why you can look at that as a sample. And then so the transformation will toss it over here into some little region R. Now we're considering the entire rectangle where delta u, v, and delta u are small. So then when it gets shifted over here, this little thing has a little area. We'll call it delta A. But the bottom line is still our u. Well, anyway, the point is that we have these two vectors. Okay, and what is our u? Remember, our u is the tangent. Okay, at some point we have concluded that the derivative is just the tangent of this point. See, we have the tangent there. So then this thing is the direction of this. So that's delta u ru, and delta v rv is the length here, because this is our this is the difference, right? This is moving this far, and the result, and this is the moving this distance as result. That's the new. This is a new point and the old point. So that's the difference here. So when they are small, and if everything is differentiable, so there's nothing too weird going on, then these values are approximately the same, because the limit goes to it. If your delta u and delta v are small enough. And being that they are the same, then we can approximate the area of R. The area then is given by the cross product, as we mentioned a little earlier. Area, you just calculate the cross product of these two things, and that will give you delta A. Now that is what we've been looking for this whole time, actually. Now if that is delta A, then you take the cross product, and then when the dust settles, the cross product is let's see. Okay, RU is remember what RU is. RU is partial x partial u, partial y partial u, and RV is similar except it's partial v. So then you plug that stuff in. So you have a determinant with a bunch of partial x and u and x and v, etc. in there, and when you solve that thing, it just equal to this cross product result, where delta A can be approximated by this particular value. Okay, and that is the Jacobian. And we will look at the next definition, the Jacobian, which is written as JUV. All right, which is sometimes written as the partial of xy and partial uv. That's just a shorthand to mean that determinant right here. And then the delta area is, so then delta A approximates the, in other words, what we're doing here is trying to get the, well, whatever this is, okay? We're trying to build up the integral, right? And the transformation of the Jacobian is going to help us do that. So, okay, so that is the Jacobian. Now, the Jacobian might take a little bit to explain, but to do it is a piece of cake. I mean, strictly speaking, you just take the 4 partial derivatives, okay, of whatever it is, and then you calculate the determinant. Well, this is a 2 by 2 Jacobian, and then as you can imagine, if you have more variables, there's a z in there, and then you will have a 3 by 3 Jacobian, but otherwise it's the same thing. So please do example 5.67 and then 5.68. I think they're basically the same deal as part of your homework. Next, let's look at page 616, where we come to what the Jacobian is good for. Now remember, the Jacobian is delta A. It ends up being equal to delta A, not the Jacobian itself, but the Jacobian times a bunch of stuff, okay? Here's a look at towards the bottom of the page, where we have the double integral, right, which is the sum of f times delta A and delta, what is delta A again? Delta A, as we looked at, is equal to the Jacobian times delta U delta V. And as a result, we have this particular equation, which shows you what the Jacobian is good for. The Jacobian is good for, look at Theorem 5.14 on the next page. Well, the Jacobian just means that you do your, you have your transformation, and you calculate the Jacobian, and then you can do the integral on a different surface. That is, you went from R and take the derivative somewhere else, S, where presumably S is much nicer than R. That is, R is all twisted and messed up or skewed or something, whereas the original S is, well, it's not the original, it's what you found out. You figure out some way to transform it so that S looks much better. It's a nice little rectangle or something similar that you can manage without some weird shape that you don't know what to do with. Or even if you do know what to do with, is a lot of work. Now that all sounds very good. There's just one problem. The transformation is not easy. There's a lot involved, and which is why your book tries to avoid it while still trying to get you to do the Jacobian. And I looked in there, and it's a mess. It's not worth the trouble. So as you can see, once you can figure out how to do the transformation, the Jacobian itself is just, you just take some partial derivatives. It's no big deal. So let's wait till you learn the transformation after calculus 3 somewhere. I can't remember where you learn it, but you learn it at some point, more than once, I think, in different advanced math subjects. And once you learn how to do the transformation, then you can apply come back and apply the Jacobian nicely and know what's going on. So that marks, we have come to the end of this section. And so please do, did I mention do example 5.67 and 6.8, calculating the Jacobians? I think they are very simple. So you take some quick partial derivatives and then you're done. And then, so for homework, I prepared some homework on page 628, problems 359, 63, 67, 71, 75, 81, and 87. And so please go do your homework. It's not very many because we're skipping the part where you actually have to do transformations. But anyway, so we're just gonna do the first part of the course. And then, so please go do your field homework, and when you're done, I will talk about some of them. All right, now that you're done with your homework, let's talk about a couple of them. Problem 363, we are trying to prove if something is 1-to-1. The way you do it, you just figure out, pick 2 random points, call it U1, V1 and U2, V2, plug it in, and then figure out that that V1 equals to V2, but U1 can basically be something else, okay? Like -1 or 1, it all works, land in the same spot. And if 2 points land in the same spot during the transformation, that transformation is not one-to-one. Next, 367, same deal. We have some function, we'll plug out 2 points, and they're equal, and then what happens? If you notice that here's the relationship, so then if we put U1 is 1 or what is that? U2 is 0. Yeah, 2 different points, they land in the same spot or something. Anyway, yeah, so again, it's not one-to-one. I should also mention that this problem says something about S equal to R cubed. What does that mean? S is the starting region, R is the ending region, and R cubed means all 3D space. That is a rather confusing way of saying things, but that's what it means. In other words, both the starting region and the ending region is the entire area, okay? All of 3D space. So that's that. And the next problem, 371, I don't know, it's very short, so I'm not even gonna figure out what it's about. It's something about, I guess, maybe you're supposed to plug U and V out of this, which is simple enough. You manipulate it and then it pops out. 375, the same thing, I think. Yeah, well, whatever. The point is you plug this thing in or something, and then you have UV equals to U squared plus V squared equal to 1. That is, that used to be the transformation, what happened is it used to be a ellipsoid, and now you got ellipse, and now you got a circle. So that marks the end of this section.